Welcome to Composites modeling using numerical methods. Today we'll be discussing module 3, where we'll be using the ability of modeling effective 3D mechanical properties to simulate tension and bending. I've invited Mr. Wei, who is going to guide us through the tutorials. Let me give you a little background of what we're trying to accomplish here. One of the things we talked about was the development of elastic properties to determine them based upon the modulus of the fiber, the modulus of the matrix, if you know the fiber volume fraction. That information can be helpful in estimating the modulus along the one direction, along the fiber direction, transverse to the fiber, and then we can also estimate the Poisson ratio. We also learned the potential of being able to determine and estimate the shear modulus, which won't be perfect, but is an estimate anyways. So given the properties that we may have, E11, E22, E33, where E11 is along the fibers, E22 is transverse to the fibers, and E33 is through the thickness, the modulus in the through the thickness direction. And then we have the three Poisson ratios specified. And to remind you, the Poisson ratio will have two indices. The first index that tells you how that Poisson ratio was measured. So the first index is the loading in the one direction that caused the contraction in the second direction. And that's how you define these indices in general. You then have the three shear modulus. Shear is the resistance of angle change within the plane that you see here. G12, that's a shear modulus in the 1-2 plane. That's the in-plane direction. And that resists the angle change of a, for example, 90-degree initially oriented two vectors like that. And this shear will try to prevent the angle change between those two vectors. So we can specify the ply properties at the lamina level, which can be measured using ASTM standards, as discussed in a different video. But one of the things we like to do is to do a couple of simulations. One of the simulations we like to do is to determine, use these properties to then specify them for each of the plies and then simulate that behavior. That's one approach. You can model every ply with one row of elements. Another approach is to be able to calculate an effective laminate engineering constants in this matter. And then I can now use these engineering constants to then determine the behavior in a homogeneous way. So we're not modeling every ply discretely, rather we're estimating the properties using a theory that's based on Chou's theory, whose advisor was Professor C.T. Sun. This approach allows you to estimate these properties. You can then provide those properties to this laminate. And the idea is that by doing so, the behavior of this laminate will be similar to the one on the left, where I did specify every ply properties individually. And I simulated every ply separately. The other model we'll be doing is we'll let ABAQUS or the software to do the effective calculations for you. And we'll use the same approach on the right, where we'll simulate a single row of elements and then let the software decide how to do that. So these are the learning objectives. We will use the 3D effective properties from Chou's theory. The Chou's theory, I'll put a description and a link, but I go through that theory in extensive detail, and we'll then use the 3D effective properties using Chou's theory. I had a former student that coded it up in Excel, and so we're going to use that Excel sheet to then calculate these effective properties. We'll then model a 3D laminate using one row of solid elements. The second approach we're going to use is, instead of us using Chou's theory, we'll let ABAQUS do the calculation for us, where we'll still use a one row of solid elements, but ABAQUS will be used to model a 3D laminate with one row of elements. So these two are very similar. The first one, we're doing the calculation ourselves. The second one, ABAQUS is doing it for you. The third model we'll be looking at is that we'll model every ply with one row of solid elements, and every ply will specify the ply properties and the angle for that ply. So that's basically simulating the left side here, and then we're going to then finally model a 2D model. So that'll be a 2D plate theory with shell elements alone. It's 4 elements. And the idea here is that we'll use classical lamination theory, which I'll also put a description and a link if you want to learn about that theory. And this approach also allows you to model all the plies within that shell element. Model number 4 is computationally efficient, and you're able to then do a good job there. So let's look at what we plan to model, and I'll give you a preview on how to use Excel sheet in a second. So the tool, we're going to just go ahead and provide a laminate stacking sequence in this example. The stacking sequence provided here at the top is a 0 plus minus 45, where this is repeated twice, 90 plus minus 30 repeated twice, and then 0, and then it's symmetric. The cured ply thickness is as given. We're going to look at the AS48552 unidirectional composite. I've given the ply properties here. Let's just presume for a second that you either estimated them by using spec sheets, or you actually did the STM standards that will allow you to measure each of these properties the best possible way. So what I'll do is show you how to use an Excel sheet, which I'll also provide in the link. So let's go ahead and look at that. So let's see how we use the tool. This laminate homogeneous properties tool. What it does, it provides effective properties given ply angles and materials and the ply thickness. You can see here that I'm in this tab here called laminate lam1. And in this particular case, I have selected material ID1, and those properties for the material ID1 are provided in laminate definition here. So let's go to laminate definition here. The material IDs, I have 6 different material systems that are provided. I will not advise you to use these properties for design because these were estimated based on spec sheets. But these are 6 popular materials that are useful. And so what you're going to do is under material ID, you're going to select which of those you would like to use. You could use, you could have even a combination if you wanted to of different materials. That's a hybrid laminate system, for example. And you can have different thicknesses as well. In the 4th column, you will enter the stacking sequence. And so you can see here that's put the 0-degree ply against the mold. And it's a symmetric layup, similar to, is exactly the laminate stacking sequence that we provided in the slide. And all you have to do is, once you provide all this, make sure there's an end here, so the software knows to read all this data here. And once you're done, you will then hit the calculate homogeneous properties. And what that's doing is providing us the properties, the effective properties of that laminate along the X, Y, Z, those modulus. You can also produce an ABAQUS or Nastran input deck, but here you can see that it's provided us EXX, EYY, EZZ. Also gives us the Poisson ratio, and you can see here the Poisson ratio is quite interesting. It's 0.603, which could be unexpected for you, right? It's greater than 0.5, for example, which is interesting. But with composites, you can have even negative Poisson ratios in many cases. So with that, we'll then go back and look at what we have next here. I'll then pass it over to Mr. Wei, who is going to guide us through the tutorial. We're going to do a virtual test number 1, where the loading is applied in the X direction, as you see here on the left. We'll then apply a load in the Y direction, and then we'll apply a load that's a bending load, and we will then compare the different models we have and see what we get. Now, you will expect model 1, this model here, the effective properties with one single row, to not as accurate as if you model every ply. And the reason is because we're only using one row of elements. And since we're modeling one row of elements, you expect a little bit stiffer behavior. A C3D8I is an incompatible bending element that allows you improve the bending performance of the element. With that said, I'm going to just, without further ado, pass it to Mr. Wei. Thank you so much for helping us in this particular tutorial. And I'll see you in the next tutorial, module 4.
Hey everyone, this video will tell you how to simulate laminate with the 4 methods. The first method is to use Chou's theory in the 3D model. The second method is to assign the composite materials to the structure and then assign the different layers with different angle. The third method is to treat the different layer as independent solid elements, then assign the same material but different angle. The fourth method is to use a 2D model. We are going to use shell elements. So the first one is use the 3D model. We are going to use the 3-dimension full integration incompatible element type. And the last one, we are going to use the shell elements. Okay, here is the material properties. This gives the information about the laminate. We have 22 element, 22 layers, and they are symmetric structure. And each layer is 0.009 inch. This is for the composite material properties. It's an anisotropic material. And this is based on Chou's theory, the effective properties listed here. And then we have 3 tests. The first one, we are going to do like similar to the uniaxial tension in X direction. So we can calculate the modulus to compare the modulus in X direction. The second test is to apply the lateral the loading. So we can calculate the modulus in Y direction. And the third test is to add this the cantilever beam. We are adding the edge force at the end of the beam, and then check the deflection, whether this 4 method can give us a consistent results. Okay, let's start it. Here I'm going to create a new model. Let's call it a model 5. Okay, so here I'm showing the first method to use the Chou's theorem. So I will create a solid one, extrusion method, the 3D. So here we can just create a 1 by 1 square and make depths about 0.2 is good enough. Right. Then we can create some material property. So we choose the elastic material property, and here we choose the engineering constants. Then we can input all the material properties in it. So based on Chou's theory, we input the effective parameters. Okay. Then we're going to assign the material properties on it. And because it is the anisotropic material, we need to assign the material orientation. So here we can choose the coordinate system, and the rotation is based on the x3. And angle, for now, we can just like this. If you want to rotate the angle, you can input a parameter here. For example, you want to rotate 90 degree, so you can say the x1 direction is rotated to here. But now we don't need it, so we just make it the same as the coordinate system. For step, we just use the static generalist and then make all the things as default. Okay, here I want to create a two reference point so that it's easy for later our calculation. So I create a two reference point, then make them set. Okay. Also, we want to create a set at the surface that can later we uncoupled with reference point 1 and reference point 2. Okay, now we want to couple this surface to reference 2 in y direction, and then the base surface to reference point 1 in x direction. So we are going to create a constraint, choose equation, then coefficient, make the surface 1 with the reference 1 in x direction, create another constraint, make the surface 2 constraint with reference 2 in y direction, so they can move together. Double check whether we input is correct. -1, open, correct. Then we are going to create the boundary condition. So in test 1, we are going to tension in x direction here. So we can create a symmetric boundary and here in x direction, and also create a symmetric boundary. And then we use displacement control. We can stretch this surface 10%, so that will be 0.1. Okay, then it's the mesh. So for the mesh, we want the element through the thickness is the same. So the mesh type, we are going to use a sweep. And then for the element size, we can make like a 0.05. Then click mesh. Then double check the element type. So as I said, we want the incompatible mode and also the 3D structure. So finally, you will see the element type is C3D8I, the same as the select shoes. Okay, that's done. Then we want to calculate the modulus. So we want to output, when we get the results, we want to output the reaction force at reference point 1. So we can calculate the stress, then we can calculate the modulus. So we want the reference 1, only the reaction force. So you click the history output request, and then go to the force reaction, expand it. You can choose all of them, but actually we just need a reference a reaction force in one direction. Then click OK. And that's done. Now we can create a job. Then we can call it okay, you can see the result. Now to know the stress, we click the result, history output, then reaction force 1. Then we can plot it. Then we click this one, the manager, edit, then we know the value. So this is the force. So force, then we divide the area, the cross-section area, which is 1 by 1, and then divide the cross-section area is 1 by 0.2. Then divide by the string. String is 0.1. Then finally we can get the E11 is this value. So we can list here. And then we can now do the mode 2 or test 2 mode 1 because we only need to change the boundary condition. Then we can get the modulus in transverse direction. And we go back to the loading part. Now we inactive this, apply the displacement. We create a new one, reference point 2. In one direction, or in two direction, we just also apply 0.1. Okay, so and then we need to double check the output. So now we want the reference to reaction force. Now we can submit again. And then we see the results. History output. So here is the reaction force in two directions. Then we click manager, edit for the throw. Now we get the in y direction, which is this one. Okay, this is for the mode 1 method. Then we go to the mode 2, so which is use the assign the composite material to see to simulate the under unilateral tension. So actually, I have to save your time. I have build all the model. So let's directly see the whole process. In the mode 2, okay. The first, the create part is same as the model 1 because we need a 3D model. So when we create a part, we choose 3D deformable solid extrusion. Then for the property, okay, for the property, we still use the engineering constants, but the input is this AS4 material property listed here. And this is also anisotropy. Okay. And then here start different. We are going to assign the composite material. So you click here, composite, then click solid. Then how many elements layer you want, you can input here. Here we can input 11 because we can assign the symmetric so that actually this is 22 elements. So when you create one, it will pop out like this. Okay. Then first you need to cite a coordinate system. So you can create one, use the rectangular one. Then it will ask you how to build the coordinate. Then the origin point you can set as 0, 0, 0. And then start a point to be x-axis. So you can create the coordinate system same as the global one. So which means you can make a point 00, 100 as the x-axis. And then choose another point in the xy plane. So here you can input a 0, 1, 0. Then your local coordinate, you create the local coordinate is same as the global one. So that you can choose your new created one, this one. So it will highlight here. You see this one is the same as global one. Okay. So all your direction is based on what you create the coordinate system here. Then here is the stacking direction. So stacking direction, we know it's from Z direction because Z is our thickness. So we choose the 3. Then rotation axis is also the Z direction, so it's 3. Then for the additional rotation, we don't need it because they don't have the other rotation. We don't need we will apply the individual rotation here. So here we already create 11 elements. So we'll click this on, mechanically the section symmetric. So that actually there will be 12 elements. Then for the region, we edit it, click it. Because they are the same, so we can just use edit, or you can double click it. Then choose the material one we just created. Then element relative thickness. We assume each layer is the same thickness, so we can assign 1. And then rotation angle, we can input what list here. So here means 0 angle, 45 negative 45, and then 45 negative 45 double twice, and then 90 degree. This you need to input twice, and then 0. So eventually will be 45, negative 45, 90, 30, negative 30, 40, negative 30, 0. Okay, all done. You can click OK. Now it becomes orange because I assigned a double duplicate material property. Now you have assigned the material property. That's done. And for this, in this case, you don't need to apply like a additional material orientation. Then you can assemble it. Then here I still create two reference points, just like the model 1. Then step is the same. We use the static method, and then for the output, for the history output, we create the we ask the set for the reference 1 and the reference 2 based on the loading. Like if you want to do the calculate the modulus in x1 direction, so you ask for reference 1, otherwise reference 2. Okay. The interaction still two couple. You can double check. Fix in two direction. Another one, reference point 1 in surface 1, and then in one direction. Load also symmetric setting here, and then apply the displacement control at the reference point. Then mesh is also same. Use the thread, and the element type is the incompatible mode. Then you can run the job. Okay, here I have finished the running, so we can check the results. Let me double check the thickness I applied here. So to check the thickness, I need to go to job. Okay, here I set is 0.099 thickness, but thickness in uniaction engine doesn't matter too much. So you can set like the like 0.2, the right thickness. Then we can request the reaction force here. Then we calculate it. So divide by the cross-section area, divided by the string. And finally we get this value. So it's 815 something. Okay, then next we calculate the test 2. For the test 2, we only need to change the loading condition, which means previously we set like here. Then we can inactivate, then activate then apply the displacement control at the reference point 2 in y direction. We still apply like 0.1 string displacement. And from the step, we'll request the reference 2 and reaction force in 1, 2, 3 direction. Then we directly see the results. So you can check whether you are simulating the right things based on the displacement control. So you can request the U in U2 direction to see whether you apply the right magnitude. So it's 0.1. Then we request the results in 2 direction. Okay, it's this value. So we paste here 418 something. Okay, next we are going to mode to do the mode 3. Mode 3 actually is a little bit time consuming compared to the first two because they are going to apply the material uh, for the individual parts, so that when you create the part, you need to partition it in thickness into like 22 parts. Then later you assign the material property to individual one, then get the then to finish the simulation. So and the remaining method is same. So I just show you how to partition it in the first two steps. So still you create a 3D model extrusion, still one by one. Then for the thickness, because you are going to create a 22 element, so you need to assign exactly 0.198. Okay. Then there's multiple way to partition it. So I would like to use like create a plane. Then you can create based on the plane. So the plane is in XY plane. The offside. So for the offside, 0 means here. And then the positive is in the z direction, in 60 direction. So we need to create 22 elements. So that will be 0.009. Second one is 0.018. Then 0.027. Okay, for now I just create three to save some time. Then we are going to partition it. So you can partition, click here, hold here, then partition based on the uh, this one, the data plane. Then you choose the one you want to cut. So based on this, then create a partition, then select cell to partition it. Done. The second one, wait, fourth one, okay, done. So you need to do like 22 elements like this. But I already finished this, so you can see they have 22 layers in thickness direction. Then we are going to assign a material property. So material property, the material part is the same. You are going to input the engineering constants and then input the each parameters. Then we can still use this composite method. But now we are going to create 22 layers. And for each layer, we need to pick the individual parts. So for this region, we pick this one. Next region, we pick this one. And then the material part is the same. We assign the material, which is great. And the element relative thickness is also 1. And the rotation, we just make the individual rotation like 0 based on this global coordinate. Oh, you also need to create the like the coordinates, but you can make it same as the global one. Then the most difference from the layer 2 is first you need to partition the whole structure into 22 layers and then assign the material individual separately to each layer. You can see my our highlight layer. The different region have different layer. Okay. Then we the following step is same as the first one. Create the step, the general static analysis, and also create two reference point, but coupled with each layer. So you can see I select this layer coupled with reference point 2, and also reference point 1 is this layer. And for the load control, symmetric bonding at this two surface, and then apply the displace control either in reference point 1 or reference point 2. And the mesh also use the swept. This one, so that the element mesh will be same go through the thickness. Tap C3D8I. Okay, then let's see results. Still output. So for the reference one is 0.1. Okay, now this value, cross-section area is 1, thickness is 0.09 multiplied 20, and then divide 0.1. Finally, we get this value. We copy to here. And then we go back, check the another direction. Okay, instead, oh, sorry. This value, okay. That's done our model 3. Okay, for the model 4. Model 4 is kind of different from the previous 3. We are going to use the shell mode, the shell element. Sorry. So when we create parts, we choose the 3D, then shape shell, then planar, then create it. We can still create one by one. And then that's done. Then for the property, we first input all the property in. So for the elastic, because it's shell, so we can choose the laminar, this one. So we only need to input the E1, E2, the mu12, G12, G13, G23. And then we can assign the material properties. So here we create the shell one. So you can choose the conventional shell. So here is what I did. You choose the conventional shell, and then also you can create 11 element. For example, to here 11 element, and then click the symmetric on this way. Then because you are choosing shell, so you don't need to create additional coordinate system. Then similar for the region, you can double click and or edit it, then just click all. That's done. And then material also, you just assign material 1. For shell, you need to assign the real thickness. So for here, our real thickness is 0.09 for each layer. Then rotation angle, just input it in it. And then the integration points, you make it as a 3. Then assemble it. For the step, you create the static one, and the history output also change it. Interaction is the same as the previous one. Loading. So this is displacement control. Okay, the mesh. Mesh tab, you are choosing the shear one, so it's S4. That's required in the slice. Okay. Then all done, you can create a job and then run it. Let's see the results. So the mode 1 is this value. Okay. Oh, by the way, here the layer is 22. Although we only input 11 layers, but we use symmetric, so that should be 22. Then another direction, the module is this one. Okay, now we have finished the first two tests. In first two tests, we have done the tension unilateral tension in two direction. So in general, this four methods should give you sort of consistent results, like similar results. You can say this four values, and also these four values. Okay. Now, when we done all of this, we can start to do the, oh, I forgot to mention one thing. For the third model, there's one thing you need to change. Here, the integration points. The integration points means the FEM integral in thickness direction. So here, because you are assigning the individual layer as SO elements, then for the default one is 1. You need to set it a little bit larger, like 3. 3 is good enough, so that the result could be consistent. And for other mode, the integration points 1 can calculate, but it's also better to set as a 3, so that make the result more accurate. Okay, now we have done these things. Then we are going to say the virtual 3, the bending parts. So bending here, we are going to create a plate with length 25 inches and thickness 2 inches. And one side is the cantilever beam, one side is fixed, another side where there's a concentrated edge loading, like 100 pounds. Okay, now we go back to our file. We can copy this file and then create a new CAE file. So here's what I did. So when you finish a copy, you can make a very quick change to fit the results. You can also create a new model based on the current geometry. If you want to build a new model, it's like this. You just create a new part, solid, and then for the model 1, 2, 3, it's like this. The length is 25. The width actually doesn't matter. You can make it as 1. And then the extrusion direction is your thickness direction. You make it 2. This is how you build a model. And then you just follow the same procedure, assign the material. If you are if you copy the old one, so you can change the geometry quickly. You expand the parts, feature, solid extrusion, click section sketch, and then you click this one, the add dimension. So it used to be 1, then you can click this one, and then enter the value you want. For now it's 25, so it can go to 25. And then material property assignment is the same as the first 2 tests. Okay, then you assemble it. Don't forget to add the material orientation here. You need, because this is the anisotropic material, and when you finish all these assignments, you need to create the material orientation. Okay. Then step is the same. Okay. Then for the step, actually we don't, for now we only need the deflection. We don't need the reaction force, so we can inactive the history output. Then for the interaction, for now, actually we don't need any reference point, so we can delete all of them. Okay, we can delete this. And for the load, okay, for the load boundary condition, it's slightly different from the virtual 1 and 2. So first, we want to assign the fixed boundary here. So you can create like this. You can create displacement control, and then choose this surface, and then click all on. Alternatively, you can also assign the symmetric boundary condition, and then click this, encastrate. Okay. Now I also assign the symmetric boundary at 2 sides. Here, the 2 sides, this side and this side. It's a symmetric boundary in y direction. You can see this one. And then for ABAQUS, actually we want to apply the edge load. But for ABAQUS 3D structure, there's no such option in the load in the create load this part. So then instead we can apply the concentrate force, which means node force. So at least we first create mesh and then assign the load. So for the mesh part, we just create mesh. We can still use the swept. And then the element type is all the same. You need to be very careful about the seed control, this one. For example, here, I make a size control. So the element size is 0.5. Then the edge. Then here we need to check our width. Width is how we create. So here I set is 5. The width is 5. So now we can count how many elements, how many nodes on the edge. So this is the total width divided by the element size. So the node will be 11 nodes. Okay, so here we have 11 nodes. Then we are going to create a set here. Click Tools, click Set, click Create, click Node, Node Set. Remember the name, Node 3. All right. So we want all the node at the top surface here. This part is our fixed end. This is our free end. Then we click OK. Then we go to load. Okay. Then we are going to apply the load control. So here is the edge force. That means 100 pounds per length. So now we have 5 units. So the total force is 5. Then it distributes to evenly to each node. So how many nodes we have? 11 nodes. So the concentrated force at each node will be 45, 45, 45, 45. Okay, we go back here. Then we create the concentrated force. Set. We choose what we have created, set 3. Then here we use negative 45. Now you can see the force is located here. Okay, this is how you apply the edge loading. Then finally we can just run the cases. So for this one, we can say we can calculate. We can ask the deflection based on this. We choose displacement, choose in 3 directions. So it's a negative 0.08211 something. So we just 211. So this is our deflection based on the mode 1. Okay, similar for the mode 2, because it's solid. The material assignment is the same. We just assign the previous procedure is the same as this unilateral tension, the test 1, 2. The difference is the geometry and the boundary condition. So we can go to boundary condition. Here, similar. We assign a fixed boundary here, and then assign a symmetric at 2 sides in y direction. And here the loading, same. We first mesh it and then create the sets here, and then go back to the loading. Create a concentrated load. Sorry, should be this one. Create a concentrated load. So it will be here. Then this value is different. Why? Because in this case, I make the width is 1, so that the total force at this beam will be 1. Then how many elements, how many nodes along here? We can double check the mesh. So here the mesh will make it 0.05. That means we have 21 nodes in one edge. So that will be 21. Then the force will be 4.761. Then we set the force here is negative 4.7619. Then we run it. Check deflection. So this is negative 8246. Negative 2486. And then for the mode 3, also, okay, for the mode 3, it's really time consuming because you need to create a really 22 elements here. And then material property and assign the individual one. You need to assign the individual like 22 elements and then give the material to different layers. Okay. Then the force set is the same as the other two 3D model. Then we can directly see the results. It's negative 8.9692. Okay. Then last one is a shell. So shell, we create the 3D shell planner, and then you can set a 25" in the width, in the length, and then width doesn't matter. You can set as 1 or something. Property here, you need to be careful about the thickness setting. So the other is the same. What I mean is you can create conventional shell, and then you can choose 11 elements or 22 if you want to use. You can just use 11 elements and then create it. Go and find and click the symmetric on. You need to care about the thickness. So actually, we assume the individual layer have the same thickness. So total is 2 inches. Then they have 22 element. And finally, you will get each layer will be 0.09, 091 inch thickness. Now here you need to change. It's different from the first two tests, which the thickness is 0.009. And the remaining is the same. Then you just assign a different angle. So here you can also see your angle setting. Then assemble similar step, just use the static step. We don't have interaction for the load. Okay, for the load, for the shell, it's actually easier than the 3D model. We first give the fixed boundary at one end here, and then give the symmetric boundary condition at these two sides. So in y direction, the other one is this in y direction. And then for the load, we can choose the shear edge load, and then choose the end at here, and then assign the material properties. Negative 100, traction is transverse. Traction is defined unit undeformed length. Okay, then click OK. Then we can do the mesh. Just do the normal S4 mesh and also just a structural one. And then we can run the job. Finally, we can check the deflection. So it's -856. Okay, that's done. So the virtual text 3, you can also get almost similar consistent results for these three methods. Okay, that's all about the simulation for the laminate in this three virtual test. Thank you.